Hello and welcome to Tribe Topper. In this video session, we are going to discuss some problems based on displacement, velocity and acceleration of simple harmonic motion. So our first problem says that a mass on a spring is oscillating with a frequency of 0.2 Hz and amplitude 3 centimeters. What is the displacement of the mass 10.66 seconds after it is released from the top? Now first of all, since the mass has been released from the top, so the equation that defines the instantaneous displacement for this mass would be x is equal to x naught cos of omega t. This is the equation which represents the instantaneous displacement of this mass as it starts from the top. Now what do we have as x naught? If you look at the question, amplitude is given to us already 3 centimeters. So x naught is 3 centimeters and frequency f is also given to us 0.2 Hertz, and the time after which, or the instant at which we want to find out the displacement, is 10.66 seconds. So that is t, 10.66 seconds. So before we substitute everything else, we need to evaluate omega. So omega we know is 2 pi f. We have done this relationship earlier. So just substitute 2 pi times f is 0.2. So 0.4 pi. Knowing all the values, we will just plug them in the given equation, in this equation, and we get what? That displacement at any instant, or the displacement at 10.66 seconds after the release, is going to be x is equal to x naught, which is 3 centimeters. So I'll just write it as 0.03 meters. Remember to convert into SI units, times cos of omega t. Omega is 0.4 pi times t, 10.66. Just put in all the values in your calculator and you get the answer as 0.02 meters or 2 centimeters. So when the bob is released from the top, so at 3 centimeters, after 10.66 seconds from the release, it is at a displacement of 2 centimeters. Okay, our second question says that on a sheet of graph paper, sketch 2 cycles of the displacement time relationship for a simple pendulum. So when they say 2 cycles, that means they are expecting you to draw 2 waves, 2 full waves on the displacement versus time graph. Assume that its displacement is a maximum at time 0 seconds, and on that graph you have to mark on the graph a time for which the velocity is maximum. We'll label it as A. A time for which the velocity is 0, we'll label it as B, and a time for which the acceleration is maximum, we'll label it as C. So let's first draw the graph, which is displacement versus time graph. So here I have drawn 2 full waves starting from 0, because they say assume that its displacement is a maximum at t0. Sorry, so we won't have a sine wave, we have to draw a cosine wave for this. Right, so you understand how we can make that mistake? That we have to draw the wave keeping this thing in mind, that assume that its displacement is at a maximum at t is equal to 0 seconds. Now this way we have time in seconds, and this way we have displacement x in meters or centimeters. Now here we say this at t is equal to 0, we are starting from the maximum displacement. So mark on this graph a time for which the velocity is maximum, and we have to label it as A. As we have already learned that in case of a simple pendulum, while crossing, like when a pendulum is oscillating, so at the extreme positions the velocity is 0, and at the mean position the velocity is maximum. But it will be maximum at this position, not here, because it is going towards the negative direction. So we have to say this side when it is going towards the positive direction. When x is going in the positive direction means it is directed to the right, so it will be a maximum velocity. So we will label this point as A. This refers to mean position, right? The blue line refers the equilibrium position, and when displacement is 0 at the equilibrium position, our velocity is a maximum, so we label it as A. Now they say a time for which the velocity is 0, label it as B. The velocity 0 when the displacement is at a maximum. Now when the displacement is maximum, that means this point, so we label this as B. So corresponding to this maximum displacement, your velocity is 0. And the time for which the acceleration is a maximum. Since we know that acceleration is proportional to negative of x, so when your x is at its maximum, the acceleration has to be also maximum, but it will be positive maximum when your x is negative maximum. So at this point, when my x is negative maximum, my acceleration would be positive maximum. So this point corresponds to C. So that means this time C. So A, B and C, the instance where the velocity is maximum, velocity is 0 and acceleration is a maximum respectively. Okay, we move on to our third problem, which says that the graph in the figure shows the displacement of a particle from a fixed equilibrium position. So with time, this is the displacement of a particle. So we have a graph here which is showing the displacement of a particle from a fixed equilibrium position. So this is your equilibrium position and the displacement at each instant. So this is a displacement versus time graph. So use this graph to determine the period of the motion. So how do we determine the period of a motion from the graph? Well, it's quite easy. If you see here, what is time period? If you remember the definition, time period is the time to complete one full wave. So as you can see, your one wave starts from here and it ends here. So that's one complete wave. And in how much time that happens? 0.2 seconds, because on the x-axis you have the time. So the time corresponding to the end of that first wave is 0.2 seconds. Therefore, the time period of this wave is simply 0.20 seconds. Further, they ask you on a copy of this graph, on the same graph, mark a point where the velocity is 0 and we have to label that with letter Z. So you can place the letter Z anywhere, because wherever the displacement is maximum, the velocity is going to be 0. So we can mark here corresponding to this point, wherever your displacement is at a maximum, your velocity is 0. So you can put Z anywhere corresponding to maximum or minimum velocity. That means on either side, maximum or minimum displacement will give you 0 velocity. Now they ask you in the second part, mark a point where velocity is positive and has the largest magnitude. Now when we want a positive velocity, it should be directed to the right. So a positive velocity means it is directed to the right. So we would say here that your velocity is positive and maximum when the displacement is 0. So going from this end to this end, you cross it, you're going towards the positive displacement. That means you're going to the right. So this point, which is 0.15 seconds, that corresponds to the maximum and positive velocity. Similarly, here again, you can have that will be 0.35 seconds. That will also correspond to a maximum positive velocity. Now for the third part, they say a point where the acceleration is positive and has the largest magnitude. The acceleration is positive and maximum when the displacement is negative and minimum. So it is proportional to x. So where is my x? Negative and maximum in the negative direction. So it is this point and this point. So that means corresponding to the point 0.10 seconds and 0.30 seconds, your acceleration is a positive and a maximum. So this is how you read the graph from the relationships between the displacement, velocity and acceleration. I hope this video was helpful. That's all in this video session. In our next video session, you are going to learn about phase and phase difference. Thank you for watching.